I'm here to present the impact of interaction context on the student-affect learning relationship in child-robot interaction. In education literature, we know that student affective display and learning have an effect on each other. Affect has the potential to foster or hinder learning. Its relationship with learning depends on the interaction context in which affect is exhibited. However, in most child-agent interactions, this affect-learning relationship is often oversimplified. Affect observations are only made during certain contexts. In addition, positive affect is often associated with positive learning outcomes, while negative valence is often perceived as a hinder to student learning. Prior work barely interpreted student affect with respect to the interaction context that the child and the robot are in. Instead, a single model or a robot behavior policy was applied across different contexts. When a robot interacts with a child, there are different interaction contexts that may potentially impact how children learn. In general, we classify them into two categories: robot role, such as a robot tutor, a robot tutee, and micro and macro sub-events within a learning interaction session. Our paper aims to investigate the affect-learning relationship in the above interaction contexts. This is the first comparative study to investigate how robots' social roles and varying level of sub-events impact this affect-learning relationship. Second, we present a comprehensive evaluation method to extract children's facial affect and analyze the relationship. Third, we present proofs that both robots' social role and sub-events within interaction modulate this relationship. We design a turn-take interaction between the child and the robot. They take turns when playing the word quest game on a tablet. The word quest game is a literacy learning game similar to the classic I Spy game. The game sends out different missions, and each game mission contains one target word that the child needs to learn. The child learns its meaning by finding the object that matches the target word in the mission on the tablet with the robot together. A game mission takes multiple child-robot turns to finish. In the tutor role, the robot knows the meaning of all words, behaves as a tutor that demonstrates knowledge to the child. In the tutee role, the robot behaves as a novice peer who lacks the knowledge of all vocabulary words. It is less competent than the child, but it's eager to learn. Our child-robot interaction contains multiple distinct task events. We extracted 5 levels of task events, representing a wide range of a time period in the learning interaction. The entire robot-child term is the top-level event in pink. Then we broke it down into robot's turn and child's turn in cyan. Then we broke the robot's turn and child's turn into 8 micro-events in yellow. The bottom-level events are 4 contingent events in green and red. Overall, the macro sub-events are highlighted in pink and cyan. The micro sub-events are highlighted in yellow, green, and red.
Can you spy objects that look gigantic? Child's turn.
Can you tell me what we are trying to find? We are trying to find. Okay. Big.
Robot's turn.
Lavender is purple. Yes. Just like my friend loves lavender. Ooh, that's nice. Flower. The flower is purple. Yes. It has the color lavender.
We ran a study with 40 children between the ages of 5 to 7 from a local public school. Then we randomly divided them into tutee robot and tutor robot conditions. The experiment consisted of 2 learning sessions and 11 game missions in total. Children's vocabulary learning performance was measured before and after the learning sessions, using a vocabulary test similar to PPVT format, where the child is asked to answer the questions by selecting one of the 4 images shown. The table in the slides shows children's pre- and post-test vocabulary scores. We built a data pipeline to extract contextualized affect features and analyze its relationship with student learning. The first step is affect detection. We video recorded children's facial expressions during learning sessions using a front-facing camera. Children's face-based affect was measured using FDEX SDK. After extracting raw affect estimates from the videos, we constructed a dataset of 440 mission episodes. Each episode corresponds to a child working on a quest mission with the robot. We have 40 children, and each child learned 11 words. Then we filter out the mission episodes with low quality. The third step is to extract 15 sub-events, and then aggregate affect vectors across each sub-event into scalar values. Regarding the aggregation method, we selected 4 methods commonly used in signal processing. Then we obtain 450 contextualized affect features at each robot child term given 30 affect metrics and 15 sub-events. Lastly, we calculated correlations between each contextualized affect feature and child's vocabulary learning. We classified our 4 hypotheses into 2 categories, robot role and micro-macro sub-events. The first main finding is that different contextualized affect features are significantly correlated with vocabulary learning depending on the robot's role, tutor, and tutee. The second main finding is that different contextualized affect features are significantly correlated with vocabulary learning depending on micro and macro sub-events of the interaction. Looking into the effect of role, more specifically, we saw that 64 and 9 contextualized affect features were significantly correlated with learning in the tutee and tutor condition, respectively. Interestingly, in the tutee condition, more affect metrics were significantly correlated to children's learning than in the tutor condition. This could be because when a robot is a tutee, it does not directly coach a child, so the child's affect exhibited in the interaction with a tutee robot becomes more crucial for their learning. To know which specific affect features correlated to which specific robot role and its sub-events, please refer to the paper. Lastly, we analyzed the distribution of affect learning relationship per affect metric, as shown in the plot. The y-axis corresponds to the affect metrics. The x-axis corresponds to the correlation strength from -1 to +1. Each dot is a correlation score between a contextualized affect feature and student learning. The dots are in the green area have significant correlations with learning. As you can see, most affect metrics have both positive and negative correlations depending on the sub-events where the affects are exhibited. We also find that the negatively balanced affect metrics, such as disgust, smirk, were positively correlated with children's learning outcomes in some sub-events. Given all presented findings, we have a few takeaways as design guidance on future educational robots. First, affect plays a greater role in children's vocabulary learning when children interact with a tutee robot than a tutor robot. Second, children's affective display during micro sub-events can contain very rich information on their learning to predict their learning outcomes. Lastly, the affect learning relationship is not predetermined, as an affect metric can facilitate or inhibit learning when displaced in different micro and macro level interaction events.